Hello and welcome to Fouraye Education. Today I'll be teaching financial mathematics. Last episode we learned a little bit about Brownian motion. In this episode I want to expand on the idea of the quadratic variation of the Brownian motion. Now quadratic variation is a very important concept at which we need to understand in order to be able to do Ito calculus and Ito integrals. So, the quadratic variation of a Brownian motion. Now, assume we have a Brownian motion omega t and assume a timeline from 0 to t. How do we compute the quadratic variation? Now, looking at the quadratic variation, we can write it in different forms. Most commonly, omega of omega of t, or d omega t, d omega t. Now this is the shortened version of the quadratic variation, which is used within Ito calculus. But currently, since we're not doing Ito calculus, we'll be using this notation. Alright, so to proceed with it, we have to partition the timeline. Imagine this line, starting from t0 to tn. We segment them into different times. Alright, so what is the step length over here? Assume we have an integer m, and we say that the step length is t over m. Alright? So, now that we've defined this and we've segmented the times, we can now see how this will become useful. So, assume at t1 we have something like this, and then we have t, and then we have 2tm as such. So we have to choose m as a very large integer, because assume we're in this portion, it'll be tm smaller than t to 2tm. So if you want to have a lot of small little continuous times in this timeline, we have to choose m as a very large integer. Alright? Now that we know we have to choose m as a very large integer, how do we write the quadratic variation? So, assume a summation from I equals 1 to m minus 1. The quadratic variation would be the difference between the increments. Now, in this case, the increments are t over m, so j plus 1 times t over m minus the Brownian motion of j t over m. Now, since it is quadratic variation, we'll be taking the square. Now, what we will do now is, since we want m to be a very large number, we'll take the limit as m tends infinity of this summation. And this gives t. Now I'll explain why this gives t in the later part of this episode. But first, let's look at the first variation in order to compute the second variation of a, say, function, right? So, say we have a set of timelines, t0 equals 0, t1, t2, tn. Oops, so yeah. And this is pi n, alright? So these are, of course, t1 is bigger than t0, t2 is bigger than t1, and henceforward. So we say that pi m is equal to max of j equals 0, 1, n minus 1 of t j plus 1 minus tj. Okay? Now, we can see that as m tends infinity, pi m tends 0. As we have more little partitions, as we have more segments in our timeline, the increments between the little segments will tend towards 0 because we have so many different segments and so many different small portions that the actual increments will approach to 0. I hope you could visualize that, because now we'll be looking at the first variation of a function t. Now the first variation t of a function f. So what is the first variation? It's sort of similar to the second variation or the quadratic variation in that the formula looks similar, but we just don't take the square. And that's it. This is the first variation, right? So what do we do here? We utilize what we call the mean value theorem. If you remember, the mean value theorem states that f prime of c is equal to fb minus fa over b minus a. Alright? So how do we utilize the mean value theorem on this summation? To utilize the mean value theorem, what we do is quite simple. We'll take these out of the function as b minus a and multiply it with f prime of c, and this being this, we'll substitute f prime c b minus a into the summation by using the mean value theorem. So what we attain is that the limit of n tends infinity of the summation I equals 0 n minus 1 of f prime c tj plus 1 minus tj, where c is within the interval of tj to tj plus 1. This is a condition, of course, for the mean value theorem. Now we attain this. Now what does this mean exactly? This can simply be expressed as an integral. Let me write that again. So the limit of n tends infinity of I equals 0 n minus 1 of f prime c tj plus 1 minus tj, where c is an element of tj to tj plus 1, can be expressed as an integral from 0 to t, an integral from 0 to t of f prime x or f prime t dt, which is a simple standard or level Lebesgue integral. And you can simply solve this through standard integration methods. Now, now this is useful when we're going to compute the second variation of a function. And we'll see how that works out. Alright? So now, say the second variation, t, of a function. We're going to say the limit of n tends infinity of, again, the summation j equals 0 n minus 1 of f tj plus 1 minus f tj all squared. Alright, So we'll define t star, which is an element of tj plus 1. And we'll make it so that the equation becomes limit n tends infinity of the summation of j equals 0 n minus 1 of f prime c squared tj plus 1 minus tj squared. Now, this will be our t starred. So again, we use a mean value theorem by setting a condition and then changing the inside of our summation. Now, if you realize, we can take this part out of the summation, at least one part of it out as pi n. So what we get is that limit n tends infinity, or limit n tends infinity of pi n and the summation I equals 0 n minus 1 of f t star j, f prime t star j squared tj plus 1 minus tj. As you can see, it's no longer the square. Alright, so we attained this. Now, what is this? We can express this section as an integral. Limit n tends infinity. We can do this similarly to how we did it in the first variation. And again, we attain a simple Lebesgue integral. However, we don't really need to compute this because, as you know, as pi n tends infinity will give us 0. So in fact, this thing is 0. So the quadratic variation of a normal function is going to give us 0. But it's different in Brownian motion, and it's important to understand this because when we're integrating according to a t variable, there is no quadratic variation, so we can simply integrate it through standard integration methods. But if you want to solve an Ito integral involving integrating according to a Brownian motion involving d omega wt, we can't simply integrate it through simple integration methods because there is quadratic variation, and I'll show that that quadratic variation for the Brownian motion is in fact t. Now, omega, the quadratic variation of the Brownian motion is t, of t, is t, as almost surely for all values of t bigger than or equal to 0. Now, to start this, we'll say, let's say q pi n. We'll define this first. Oops, it's gonna be n, yeah. And since it's quadratic variation, we square it. Now, if you look at the expectation and the variance, which is quite simple to compute, so I will not showcase how we compute it. If you look at the limit as n tends infinity of the quadratic variation, we'll see that the expectation tends towards t t as n tends to infinity, while the variance tends towards 0. Now, these two are pretty easy to find, so you can just work it out yourself. But through these two, I will construct a Chebyshev lemma. So I can't exactly pronounce it, but yeah, so we'll have as such, if we construct our lemma, is going to be smaller or equal to 1 over n squared, n squared in fact, n squared of the variance of q pi n. So, if you look at this, and we make it so that the limit tends toward infinity, this will give us 0. Right? So what we'll do is then, now that we know that it'll give 0, we'll take the case where it's equal to 0. So limit n tends infinity of q pi n minus t bigger than 1 over n is equal to 0. Now, how is it equal to 0? What we want is that q pi n tends towards t in probability. And remember, q pi n is simply the quadratic variation of the Brownian motion. Therefore, we can simply say that the quadratic variation of the Brownian motion is equal to t, almost surely for all t values bigger than or equal to 0. And that is basically the quadratic variation of a Brownian motion. And now that we see that the Brownian motion, unlike a normal function, has a quadratic variation of which the value is t, whereas a normal function has no quadratic variation, has 0 quadratic variation, we can see that it's not very simple to compute an Ito integral or an integral involving Brownian motion, because we can't use standard integration methods. So I'll show you how you can compute and how you can think of the Ito integral in the next episode.